Okay, Math 1101. This is the lecture for Tuesday, November 24. And I thought today, since we finished all the slides, I realized there's a lot of material that the book has to offer, including even more material. And I thought I'd go ahead and share some of it with you. And so this will not be the slides. It's basically, what you can see yourself in the online book, or for some of you, actually the real book. But what we can do is take a look at some things that may have been missed or maybe need to be reviewed. So today's lecture, I thought I'd go over and do an overview of Chapter 6, which is going to be a big part of the final. But of course, it's a cumulative final, as I've said a few times before. But 6 will take up a more than its share, because it's the later material. It didn't get the advantage of a midterm. And I'm not prepared to give you a midterm before the final. I've heard of some teachers doing that, and that just seems like excessive work for both the student and the teacher. So I just slightly emphasize the later material, and that seems to take care of it. So overview is a good thing. And next week, the Tuesday, will probably be recorded the way it looks now, and I'll be going through a chapter quiz, the Chapter 6 chapter quiz. There's a bunch of problems there in the back, and if you'd like to start working on them now and see how I've solved them, you may do so. So then the last day, the 3rd, will be live, and we'll talk about whatever you want to talk about, essentially, as far as the test is concerned, and I'll have a few extra problems to talk about and some ideas about the test. It's a full 120-minute test, probably the same exact format as before. Plenty of multiple choice, but some that are not. Let's take a look at standard deviation. They've shown most of the work here, and let's take a look. We did something with Clayton Kershaw and another pitcher before, but they updated it. Madison Bumgarner was pretty hot for a while, and John Lester, the Chicago Cubs. They had ERAs that went through the years, and I know Kershaw had a lower ERA, being a Dodger fan. I noticed these things. So anyway, they go through and they pick the years from 2012 to 2016, and they find the mean for Bumgarner, who was with the Giants, had a mean ERA, earned run average, the average number of runs that they give in a 9-inning game, not counting errors, and 3.36 is still way above average. And standard deviation, which is the measurement of variability, 0.89. What comparisons between Bumgarner and Lester can we make? And so let's see. Here we've done Lester. I misspoke. Lester is given at 3.36 with a variability number standard deviation of 0.89. So the mean is very easy. You just get all the numbers and put them in your calculator and divide by 5. And so they've rounded it a little bit. Well, that causes other errors we don't need to go into, but let's not worry about it. 2.96 is better, less than 3 runs a game as compared to just over 3 runs a game. So Bumgarner was doing very well for those 5 years. But we'd like to find the standard deviation. So you should plan on this on the test, and it's not going to be one of those multiple choice problems. I will try to give you friendlier numbers than the examples I'll probably be presenting to you. Here we have decimals. Sometimes we have numbers that are very large. But I think it's just a good idea to expose it to you so you just don't take it for granted, which is what, unfortunately, a lot of people do. And so if you can do these examples, you should be fine with the final. That's the way I look at it. But anyway, we find out how far each of these years of ERA, earned run average, departed from the mean. The first year was 0.4 above the mean, which is not good. Below the mean is very good. In fact, 4 years in a row is below the mean. So he just had one sort of off year in 2012. And all the others were much better. They're all the 2s, so they're all below average. How about that? 4 years below average, which is better. Well, they're very close to 0, you notice. And then one that's above average. Well, the idea is once you find the deviations, you go ahead and square them. There should be 4 decimals. They've rounded these numbers again. And these numbers are so close to 0, they're just going to call it 0. And this number is also quite close to 0, but it did register a little bit. Anyway, they add them up, and they get the sum of the squared deviations. So this kind of removes the minus sign and also kind of puts little squares. The other class was quite visual about showing these things. They show a little line. They show squares on top of the line and all that kind of stuff. We don't need to go there. We'll just go to the step-by-step process, kind of a cookbook situation. And I'll try to avoid decimals entirely, or maybe just have tenths. I will not go to hundredths if I give you data with decimals on it. And so we sum it up. We divide by 5 One of the footnotes in your book will say you could divide by n minus 1, but let's not go there. That's a separate situation. That's very popular, but we're just not going to worry about it. This is the actual standard deviation. So we divide by 5 and then take the square root. They did not do that step by step. You could show an extra step there. I'd appreciate that, especially if you make a mistake. And the more work you show, the more willing I am to overlook minor mistakes. But if you don't show me any work, then of course it just takes over and you lose almost all the credit, or perhaps all of it if you don't show me any work. This is the type of thing I would need to see the work on. This is why I thought I'd lead off the discussion with this. Anyway, this standard deviation is only 0.22. That's very, very consistent. The teams like that, even if somebody's a little bit worse than this, the consistency would be something they could hang their hat on. Whereas this guy, Lester, he had a much higher standard deviation, 0.89. So you kind of take a look. There's a 4, there's a 3, there's a 2, there's a 3, there's a 2. Yeah, he's all over the map. This is like double what that one is. So yeah, he had high variability. That's why they probably picked him. Well, anyway, they have some more comments here, and they talk about what they just did. I kind of explained that already. And square the second column to get the squares of the deviations, and et cetera, et cetera. Anyway, Baumgartner was a better pitcher over those 5 years. And also he had a smaller ERA, so he was consistent, good and consistent. That's like the best of both worlds, I guess. But Lester was not bad, but he was not consistent. He had a much bigger sigma. Sometimes it's called S. Okay, well, anyway, let's move on. We've already looked at the free throw example. Some of these made it to the slideshows, and some of them have been updated in the 3rd edition, but that's not worry about that. Let's move on. I'll continue turning the pages for a while. I wanted to get into 6.2 for another side comment that I thought I'd fill you up with here. There's 6.2, the bell curve. So it's kind of an overview of chapter 6. Stuff that, who knows, might even show up on a test or something. So let's see, that's what page number are we talking about now? That's 415. I'm looking for page 425 for my next comment. Well, actually, I did have something here that I wanted to say a little bit about. We did have the SAT verbal scores, and apparently they range from a low of 200 to a high of 800. And we see the percent of students that land in each of these ranges. And it turns out, especially if they plot this, yeah, there it is. It looks an awful lot like a bell curve, and they even put a bell curve over that. And that's something I just finished doing in my 1201 class. They actually have the computer commands to do that with the R language, but that's beside the point. That's a much more difficult class in several ways. But the point is, it's still settling in like a normal curve. An average score, 450 to 499, has the most number of students and the highest percentage. But look, it's got very close competition at the 500 to 549 area. But the ones that are very high or very low are pretty rare. Bottom 1%, upper 1.8%. This does add up to 100%. And at that point, there was 1.4 million students or so. And the mean was 507, which explains why the 500, well, you'd figure the 500 group would have the bigger number, but it doesn't. It actually slipped just a little bit, but this number 507 is very close to 500, so that's not terribly surprising. Plus, this is almost a tie, so to speak, so that's not a big deal. Standard deviation is not at all obvious, but anyway, you can see the picture that you see there, 6.2. So let me continue, and they talk about, anyway, let's move on. Let's get to some stuff that we have not seen that I felt like talking about. And let's get down to page 425. It takes a little while since I've got this expanded a little bit. Oh yeah, I did want to say something about this. Percentiles, in case you're unclear what percentiles are, especially as they relate to a normal curve. The 50% mark of percentiles is exactly average. They're using the word median here. They could easily use the word mean, because the mean and the median are the same in the normal curve. But something we've also looked at, especially as far as box plots are concerned, the Q1, the 25%, the bottom 25% of the data, the end of the first quarter, so to speak. If you were to place that on a normal curve, that's what it would look like. It may not look like it, but that would be a fourth of the curve because it's moving pretty fast up here. This second quarter is moving quite quickly, also shown about here to the halfway mark. So that would be the 25% mark. The 75% mark, that would be symmetric with the 25% mark, but don't worry about it. That's the end of the third quarter. And then if we pick some number out of the blue, the 91.6 percentile, it moves even further over. That happens to be a score based on something that we may have talked about before. Well, maybe we didn't, but if you pick a number 660, there are ways to find out that it happens to be in about the 92nd percentile. That is, this person is ahead of almost 92% of the scores, with only around 8% left. So that's a very good score. Anytime you're in the 90s, that's quite good. Unless you have to have a 99, then you'd be very disappointed, I guess. You'd ruin your 4.0. Here's a table that you will get on the test. You will not have to worry about it. I will supply it for you. And okay, the only comment I would have is sometimes you just round out the nearest tenth, but just do whatever you feel comfortable with. And I'm almost there to page 425, so more comments I'd like to make. Okay, so that's something we did mention, and significance of apparently small deviations. So yes, I did want to say something about that. They did mention in the slideshow that we had a very large z-score that was off the charts, and only from the difference between 20% and 21%, but the thing is, that difference of 1% over 100,000 people moved the needle a lot further than you might have thought at first. Because of the immense sample, this p should be pretty much pinned down. It shouldn't even move 1%, but when it did, it was off the charts rare, literally off the chart. The largest number we had was 2.7. So we're not going to ask you questions like that. I thought I'd quickly mention the Fallon Leukemia Cluster. Maybe this is where Jimmy Fallon is from. I don't know. I actually was there once. It's kind of like a major beginning part of Highway 50, the loneliest road in America. It goes from northern Nevada and part of Utah, and there's hardly anything there. If you see a gas station, you better get gas, because that's your last chance for a few hundred miles, it seems. Well, anyway, they did have a few comments that we do see here that I wanted to mention. And it's a little bit of reading here. We do assume that you are doing the reading, of course. We're not, assuming you're not reading this stuff, but it requires a little bit of interpretation to make the main point here. We've got 16 children diagnosed, but this is over a 4-month period, and this is a type of phenomenon called the leukemia cluster, and they have a map of it in the book as well. And we see that over a 4-year period, they had 16 children diagnosed. That doesn't sound like much. That's only about 4 per year. So that's all. But then turns out that the average rate is 3 per 100,000. And that works out to be 1 every 5 years. That is 0.2 per year. 1/5 is 0.2. So if we're talking about per year now, 0.2. So we've got to standardize what we're talking about here. And this was 16 up here, which is divided by 4. They do mention it's a 4-year period. So that's 4. 0.2 versus 4.0, that's a factor of 20. 20 times more than we expected. So 16 doesn't sound like much, but this is a rather unpopulated area. And if your rate is 20 times higher than normal, something's up. Oh, by the way, in case you want to go to Fallon, this is the map of how to get there. So I don't remember the Naval Air Station, but I guess it was there. It's been about 5 years since I've been there. So anyway, they talk about some other studies too, but the point is sometimes you have to wade through the numbers to kind of see what's going on, and the small numbers can change rather quickly. Okay, let's go over to 6.3 and take a look at some interesting stuff. We just had an election, and there's some comments that I can make about, can you believe the polls? Once again, they're saying that the polls were off, and they're never perfect. So that's number one. Polls, exit polls, or public opinion polls that are taken throughout the years, especially during election years such as 2020. This has data concerning the 2016 U.S. presidential election. So I wanted to have a few words to say about that. And yes, so we had some battlegrounds back in, well, this is 2012 even. Actually, this is 2016. So these are battlegrounds that apparently Donald Trump won each time versus Hillary Clinton. And this is 4 years ago, of course. And so they talk about even the third and fourth party candidates. My brother-in-law voted for Jill Stein. I'm not getting into politics much, but anyway. Election polling. In years past, professional polling organizations had a good record of predicting the outcomes of elections. However, and I gave this lecture like the day after Election Day in 2016, and everybody's wondering what the heck's wrong with the polls, because everybody except for the LA Times and maybe some very minor polls got it wrong. And everybody's focused on the popular election, and as you know, the Electoral College is what gets a president elected, not the popular vote. Well, anyway, they figured even in 2012 they had underestimated the popular vote for Barack Obama, which is basically trivia because it doesn't directly matter. It's like 51 elections. And of course, back in 2000, I remember this staying up late, and they projected that Al Gore had won Florida, therefore was the next president. But of course, 537 votes separated the two, and George Bush became president. And so polls are often pretty good. And I noticed the last edition of the book said that polls are very good at getting it right. Now, they modified this just a touch in the last 4 years, a little free information there. Methodology, and we've got some basic things that we've already kind of covered, the margin of error, confidence interval, confidence level. We're going to stay with 95%. I thought I'd say a few words about this topic here and see if we can make some headway with it. It probably isn't super important, but it does show something about what we have in a particular, less political example. We can count the number of red marbles in a small sample. For example, we shake a jar. Well, okay, we've got a large number of red and blue marbles. We want to know what percentage of the marbles are red. And the only way to do it for sure is to actually count all the marbles. And that's what collecting votes does, or even a census would do. So maybe impractical if there are hundreds or millions of them. Of course, that's somebody else's job to do that kind of thing. But this is just marbles, a big jar of marbles. Can we make an educated guess? How good would that guess be? And yes, we could take a sample, just dip our hand in there and grab a bunch of marbles and count the number of reds. We shake the jar, select a few marbles at random, and 20% are red. Now, we can't say from this that exactly 20% of the marbles are red. They might be, but the big question is, how large a sample size should we use? And then, what about that confidence level? Would it be 95% or what would it be? So let's pretend as if we really found out later, and we're kind of back figuring this, that 25% are red. Now, we don't know that, but that's something we find out later. So privileged information, I guess. So we draw 100 marbles from the jar. And we could show, we're not going to do it, that exactly 25 reds would be about 9%. But that's not a big deal. The idea would be to, however, look at kind of a makeshift confidence interval between 23 and 27%. That's the margin of error of 2, which we can talk about as well. And it turns out the probability of landing in this zone is only 44%. That's not a very good confidence interval. The 100 marbles does not seem to be enough. And they actually have a table. What if we pick 500? Then suddenly the probability in this little zone that we figure is successful is 72%. You pick 1,000, it's up to 87%, and you can see the progression. The more you pick, the more solid it becomes. To pick 2,500, which means you've got even a bigger jar of marbles than that, you'd be 98% sure, given the fact that we know it's 25%, right? And it turns out, believe it or not, that the actual size of the population doesn't really matter. In algebra, they essentially cancel out. So we're not going to be concerned about whether it's 25 million or 25,000. I'm pretty sure it's not 2,501. That would be found in the entire jar. Remember, these are samples, large samples. This implies there'd be thousands and thousands of them, but I'm not going to get into that. So focusing on the 2,000. They're saying that the probability is 96%, that we would be between that zone that we wanted, 23% to 27, notice 25, the exact number is in the middle. So we're kind of using our time machine here, looking at the answer and then going back and then seeing how could we create the interval. We're not showing you the details here, kind of beyond the scope of the class, but the point is the bigger the sample, the better off you are. Now we've fixed a margin of error here, 2%, plus or minus 2%. That's how we got the 23 and 27%. We just added and subtracted the 2 to the 25. So that's the idea. So yeah, so they're going to say, for example, this would not be something that a polling organization would say, but just relate it to other things. You could say with 96% confidence that the percentage of red marbles is 24% with a margin of error of 2 percentage points. Yeah, so that's kind of what they're going to say. Now, 96% is not a confidence interval we see very often. 95 is the big one that we are interested in, and that's all we're going to need. So let's move on to another subject here. Key concept, they talk about the margin of error, the confidence level, which we mostly keep at 95%. Now, here's an important point that we need to make. It's very important to notice that it is possible for the polling organization to get an unlucky or unrepresentative sample, which may have played a role in the 2016 polling debacle as far as being able to predict the winner. That's all I'm talking about. I'm not talking about politics. Say a sample with 8% red marbles or a sample with 80% red marbles instead of something that would be more typically found to be between 23 and 27. Yeah, you could get a real low number of reds or a real high number of reds, but the odds are way against that, especially with a large sample size. So yeah, we wouldn't expect it to be, from the big sample that we had, we don't expect 4% failure rate because we'd be 96% correct, but then of course 4% wrong. No margin of error on spelling tests. Yeah, and 2 plus 2 is 4. No margin of error on that one, plus or minus 0. Well, back to the polls. Let's apply what we've learned to hypothetical idealized opinion poll. And so we're going to talk about various things here. And for example, just to get this out of the way, 95% confidence that 45% of the American people support foreign aid. The margin of error is 2 percentage points, so very common level, 95%. And they're going to go ahead and add to the 45, 2% to get up to 47, subtract 2% to get down to 43. That's a very easy thing to do. So everybody should ace that on the test. Margin of error is often called M. This time it would be 2, and it's already in percentage, notice, so that could be distracting to some people. But they're saying that 70% might support the aid, although the odds are very high against that happening, I might add. But it is not impossible. And opinion polls are often taken over time and usually by different organizations. You don't have to trust just one poll. Your confidence should increase if several polls report similar results. But it didn't happen in 2016, so I did piece together some research I did on this, and from the prior book, actually, we had more information on this. There are systematic errors involved in polling, and you're not going to find this directly in the book. Kind of read between the lines here. And systematic errors involved like maybe 3 or 4 different things here. Now, the people polled could be maybe not reflective of the population. Now, institutes like the Nielsen ratings for television, they go out of their way to pick representative samples. That's something they have to do. It's like 6,000 people around the country from all races, all ages, all regions, all occupations. They just try to do the best they can to do it. And then they still report a margin of error. That's a classic case of that. But what if it wasn't representative? The elections might be more hastily put together. Maybe they picked the wrong people. Here's another one. People turn out in different proportions than expected. So maybe some people stayed home because they say, oh, Canada Day is going to win. All the polls are saying it. Why should I waste my time? And then they don't win because they didn't waste their time, and then they didn't get the votes they actually needed. Here's another one. What about being unreliable? 95% of those claiming to vote for candidate X actually voted for X. And that sounds pretty good, but what about candidate Y? What if virtually 100% for candidate Y, loyalty factor involved here, then they actually do vote for candidate Y, state by state, of course, for the Electoral College. And the other one only has maybe 90 to 95%, not quite so much loyalty. Yeah, so that's another factor. And you've got the random sampling versus self-selected, too. Self-selected is not very good. So sometimes when people pick polls that they want to reply to, that causes a bias that generally is already known about, so we do not worry about that. But I thought I'd toss those tidbits in. 4 years ago, people really wanted to hear what was going on, so I really had to dig up some stuff. Okay, let's continue and find some more material to fill in the cracks that were missed before. And so I'll look at the next section, and let's find some more here. Here's another very easy one where a 4% margin of error, just add it and subtract it to the 33% given. Do not be distracted by a different confidence level. That's something that we're not worried about. But we can go ahead and subtract the 4%, add the 4%, and there are our answers. We found about the solving for n, how large a sample would guarantee us a certain amount of accuracy. And so the bigger the n, the more accurate you are. And accuracy is reflected by a low margin of error. So that's important to notice. So if you have 1,100 Americans, our margin of error is only about 3%. You can do the math yourself. Just put in the 1,100. Don't worry about the percent. Just square root it, divide it into 100, and make sure you can get around 3%. and only 500 people are selected. I think we did this one already. That's going to give you a 4.5% margin of error. That's worse. The bigger number, the worse it is. So, and here we have 719 in a particular sample size for the poll in Arizona. This, remember, was 4 years ago, and that's when I guess Donald Trump won that state. And yeah, so we talked about the margin of error. Got some decimal places here. So you subtract 3.7% from the 45, add 3.7% to the 45. That kind of thing can be done. So I wanted to find part D. How big should the sample be? Yes, we had some extra stuff I wanted to talk about, but having a little trouble getting it. So yeah, so that's C. Okay, let's go over to what I call part F. They talk about the statistical dead heat. I don't think that that's quite as important, so let's move along. You can read your book yourself, so I'm not planning to read the book for you. I'm just trying to find stuff that may have been missed. Here's the other formula. It's really equivalent to the first formula. This time N, sample size, is about equal to 100 over M, which is squared. That turns out to be what they call the inverse of the other formula. And this, of course, is figured on 95%. And it's not exact, it's approximate. So that's another thing to keep in mind. Statistical dead heat. So here, back 4 years ago, another poll done in September of that year showed that Trump and Clinton were called a dead heat. And they're saying don't overuse that word. It really should be tied in order to call it that. And so they go through some comments about that kind of a thing. So they go through this and say that the difference between 44% and 46%, which is what apparently back then Clinton had 46% of the vote and Trump had 44% of the vote. And they're saying it's less than the margin of error, so that means it's really kind of close, but not a dead heat. So they're kind of splitting hairs here. We're saying that it really is not, we're not confident that somebody's going to win here. It's really got to be outside of the margin of error, and it is not. So, but it's not quite a dead heat. The only time it's a dead heat is when it's actually tied. They have a picture here of Clinton with her 46 in the center, plus or minus 3%, and then Trump with 44%, plus or minus his margin of error. And, you know, something like this must have happened. And so anyway, but that's, of course, once again, popular vote, which is not completely representative of the electoral vote. And there's a classic case. I very well remember when they predicted the winner of a race. I don't remember which one, at 5 o'clock in the afternoon, California time. And you don't have to vote, Sam. The networks depicted the winner, or predicted the winner, 3 hours ago. And yeah, that is sad. I heard stories from people who worked the polls that everybody left. Well, by 5:15, it was like a ghost town. And then propositions probably got swayed in one direction or the other because somebody voting for a certain candidate probably would vote yes on a certain proposition, and then they didn't show up, and then no would win. So it was a bit of a distortion. So the networks got a lot of heat for that. So now they're quite a bit more conservative when it comes to predicting winners. It took them several days recently to do that. But it's not quite statistical dead heat. So anyway, they go through the methodology of polling, and anyway, they talk a few things about if you pick numbers from a phone book. I guess they still have phone books. I think I have a dusty one somewhere. And the voting population only uses cell phones is ignored. Well, of course, if cell phones can be in the phone book too, so this is a bit of a misnomer. Almost all public polling organizations back in 2016 wound up underrepresenting Trump voters. You could be candidate A shy. I heard of Biden shy voters and Trump shy voters. Apparently there were more of those, including in 2020, where people did not want to admit it to a pollster, but they would vote for the candidate anyway. So that's what causes problems with predictions. And anyway, Clinton was widely considered to be the likely winner right up until the voters proved otherwise in enough states that Trump got more electoral votes, of course, even though more popular vote went to Clinton. And same with Bush versus Gore. Gore had more popular votes, although it was a lot closer. But of course, Bush had more electoral votes. They have a situation here. Let's see. We have something I wanted to get to after this, methodology of polling. Yeah, so that's actually, okay, right. So, yeah, they kind of dismissed that one in this particular edition. So, I guess I can do that. Yeah, they do mention this. I guess I can say a few words about this, but I'm not going to overemphasize it. This online survey about banks helping people meet their financial goals Some banks are more helpful than others, I suppose, but the point here is that the online survey is not based on a probability sample, and therefore no estimate of theoretical sampling error can be calculated. Oh, okay. So yeah, it's just collecting data, I guess. That's all. So they talk about here's the main point I wanted to get to. Um, yeah, they talk a little bit about missing landline phones. So sometimes if you just use cell phones, you might be missing the people that still use landline phones. But TV and newspapers, magazines, and other media often invite their audiences to respond to questions. Could be even radio, I suppose. And it's usually pointed out this is not a scientific poll, and you should put capital letters on that. Not a scientific poll. This is not a probability sample. These are not randomly chosen people. These are people who are what I call loudmouths. The audience of a show could be predominantly conservative or predominantly liberal, which would skew the polls. And such a poll includes only those people who watch this particular show and want to be heard. It should be viewed skeptically with a capital S. In other words, it's basically worthless in my opinion. But, you miss the silent majority in the middle. The people who don't care that much, who have slight leanings in one direction or another, they're not going to probably waste their time. They probably have better things to do. But other people, with a lot of time on their hands, they have an axe to grind, that could be a bit of a problem. So randomness of the sample is not the only problem with methodology. Maybe several sources of error. And here are 4 different ways of writing a particular question. Do you support efforts to prevent fires in national forests? Well, practically everybody would, unless you're a pyromaniac. Here's number 2. Do you support efforts to prevent fires in national forests by thinning trees to maintain healthy forests? Okay, well, I worked for the Forest Service, so yes, that is part of it. Do you support efforts to prevent fires in national forests by increased road construction to allow commercial loggers to thin the trees? Now, that's sounding a little more negative, I imagine. Do you support efforts to prevent fires in forests, even though fire is an essential part of maintaining a healthy ecosystem? In fact, we even had the fire lab at UCR, right next to UCR, I should say, and so they actually set the fires very carefully, of course. And so, yeah, that's kind of an oddity, but that is also true. But yes, most definitely people who have, and I'm looking here, right, here's a very important point as well. I wish I could put this in yellow. Valid reasons to trust, perhaps with a grain of salt, reports from professional polling organizations. That's what the margin of error is supposed to help you with, and Gallup is the one I've heard of the most. Uses random sampling, employs specialists to randomize these questions to take out bias as much as possible, have different versions and rotate them as well. Make sure the questions are properly composed, answers properly reported. But there's every reason to be skeptical of polls who do not use representative samples or are conducted by someone who has a point of view or a vested interest to support, an axe to grind, so to speak. Data that isn't real or is highly skewed in one way or another isn't really data, in my opinion. It's just misinformation. But that's just what I have to say on that. Let's move along and get a little bit of 6.4 handled as well. And here's the one we just basically talked about, but was missing quite a bit of stuff. Statistical inference, clinical trials. This one goes more into the clinical trials part versus the slideshow. So they have a little introductory item here that you could look at. I'm going to turn to my page of notes here. Just be a second. Hold on a second. So that page there, okay. So experimental design is interesting here. They talk about the placebo. You probably know what a placebo is. It's a benign substance that shouldn't affect the person in any way. Contains no medication, indistinguishable from the real drug, and a simple sugar pill is a favorite. Subjects do not know what they're getting, and often the person giving it is double blind, and they don't know either, so it removes any kind of bias. And the test results are in for a new drug. 9 out of 10 doctors recommend the placebo. Okay. And taking a placebo can create an expectation of improved health and thus result in positive medical benefits. It's called the placebo effect. That's the power of positive thinking actually at work. So they go through a few things here. I don't have to go through this too much, but they have to decide how much of a difference between the two groups, the one getting the drug and one not getting the drug, is medically important. Is 1% enough? Is 10% enough? Is 30% enough? You have to figure that out. How many subjects should be enrolled? Should be enough to matter. And then you have to put part of it in one group and part of it in the other and try to make it as close to 50-50 as possible. Sometimes that's not possible for various reasons. Or if it's by gender, make sure you make it as close to 50-50 as you can. And then we have to see if there's a significant difference. What is significant? Well, that has to be thought about. So we can take a look at some of these concepts here and see what we have in mind. Let's move on to, here's the double blind. And but sometimes you have some bias that slips in. So the double blind removes that kind of thing. The observer or the subject can inadvertently affect the results. If a researcher has worked so hard, maybe their PhD is riding on it, or a big promotion is riding on it or something, and develop a drug that she has come to believe in, such as the vaccine for COVID-19, that maybe comes to mind, but just really wants it to work, whether it works or not. And the researcher knows which subjects have been given the drug and which the placebo. The chance exists, maybe small, but he or she may inadvertently interpret the condition of the subjects in favor of the drug. And that would be a bias. It's not a huge bias, but it's enough to force double blind on many of these experiments. So we've kind of covered some of this stuff already, and we talked about flipping a coin 40 times in a row, getting heads every time. And that kind of thing could be talked about, but that's not what I really wanted to look at. Let's continue and get back to some other things. We had the try it yourselves. I didn't really have time for this, but I thought this was a very interesting one. It didn't make the slideshow. As the preceding examples indicate, statistical significance corresponds to a common sense notion. Flipping a coin twice and getting heads both times is pretty easy. But you're driving, you pass three 1951 Studebaker cars. I wouldn't even know what that looked like, but it'd be an older car for sure. Now that would be very rare. That would be significant, and getting two heads in a row is not significant. That's very, very common. Now we have an example considering the following table showing the results of a hypothetical trial. Okay, so how about the treated group, 53 improved. The control group, 50 improved. But in the treated group, 47 got worse, and the control group, 50 got worse. But the thing is, improved versus got worse, 53 versus 47 in this group, 53% versus 50% of the control group. Yes, there's a 3% difference. Is that enough? Probably not. Probably not. It's not obvious, but p-values tend to help us smooth this out. And I would imagine, since we did talk about p-values on the slideshow, which you should have seen, that this number here would be, comparing the two, would be a p-value of about a 0.3 or so. Not very significant. Yeah, there's a little something going on. Maybe even a higher p-value. They didn't tell us what that was. Now I feel like calculating it, but it's certainly not less than 0.05. This is a rather bland set of numbers. And come to think of it, the p-value might be something even ridiculous like 0.7. It's extremely common to get numbers like this when nothing is going on. You flip a coin, for example, you expect it to be 50-50, and you get 53 heads. Whoopee. That doesn't really say much at all. So they go through the Vioxx versus the Aleve and talk about the 0.02 and 0.002, I should say. And so, yeah, this is one of those where the Aleve is definitely working because, we see something that if we pretended the pills were the same, and to get a difference would be very rare. But that means that the Aleve seems to be working because of that very small number. But that's a little tough to figure out. We're not going to make it so convoluted and hard to interpret. We're just not going to go there. But I did want to talk about this example, which they did not have time to cover before. A drug that we believe may prevent colds. But now, colds don't seem to be all that important anymore. But yeah, you don't want to get a cold, that's for sure. So they're saying, we know on average 50% of people will get colds this winter. We could treat 100 patients with this drug, and we find that 55 did not get a cold. Okay, that's no big deal, I would think. Is the drug effective? Because it gave 5 more people the opportunity to not get a cold. But did this happen by chance? That's what I'm thinking. Probably just happened by chance. I wish I could draw a little bell curve here for you, but I can't. Without treatment, 50% will get colds, and 50% will not. So let's talk about people not getting colds. Let's make it straightforward. So 50 will get colds without treatment. But then with the treatment, we got all the way up to 55. Oh boy. Well, we find the p-value, 0.184, is the p-value. Well, okay, 55 is bigger than 50, and that number is not, way up there, but it's way above 0.05. We still have an 18% chance that this could have happened randomly, and 18% is way above 5%. So that says in 18.4% of observations of 100 untreated subjects, we expect that 55 or even more than 55 will not get a cold. And that 18%, that's just not a big deal. So having 55 or more staying healthy is not unlikely. It's quite likely, actually. We expect it to occur almost 20% of the time without taking a pill at all. So what good is the pill? Not much. Now, you get up to 65, now you're talking. We don't need to show the math. We're just giving you the ideas, which is what this class is about. And so to get to 65, now we're talking. That's about 2/3. And that p-value, we depended on random chance. This is just like the Vioxx and Aleve example. Now we're down to 0.2%, 0.002. And that probability that 65 or more patients would not get a cold, the drug had no effect, is not likely at all. I'm not putting my money on that. 2 chances out of 1,000? No, that's not good enough for me. Now you could do that, but most people would not. That's why the 5% is almost cast in stone as a level of rarity that most people will use. And this is rare enough, whereas this is not rare enough. 65 is a big deal. 55 is not. And it may not seem like it would move the needle that much, but it does. We don't need to show you the math, but the small p-value associated with the study suggests that the outcome is due to something other than chance alone, but it doesn't say what it is exactly. Usually we can kind of deduce what it is, but it doesn't say it specifically. So if there's more than 1 or 2 or 3, 4 different things, it's not going to say which one it is. You need more advanced analysis. For this reason, it's important for researchers to take care to avoid factors other than the drug or procedure being tested that might cause the two groups to differ. Because if you had multiple variables, that could be a big problem, and that becomes far more complicated, and we just do not care to do that at all. So a little bit more to cover. Yes, correlation, I wanted to cover that as well. Correlation and causation, they're not the same thing. Just because 2 items are correlated doesn't mean that one causes the other. It could be random chance, and they actually spell out the possibilities. And here's positive correlation between ice cream sales and shark attacks. So ice cream must cause sharks to attack. They love the ice cream so much. Well, that's not really it at all. Both of these tend to rise in warm weather. More people are swimming and more people buying ice cream, but they don't cause each other. They're formed by what's called a lurking variable, a third variable that they forgot to talk about. We did talk about the balloon already. That's not a big deal. Here we have an interesting case of alcohol use versus tobacco use. This is in British pounds, so this is not dollars. This is they've divided Britain into 10 different regions. I couldn't tell you exactly where they all are, but we want to see if there's a correlation between the 2 variables, spending on alcohol and spending on tobacco. Does one get associated with the other? And so they go through all of it, and here's the results. We have in British pounds, alcohol being spent for these people they chose, between 4 pounds and 7 pounds, and the tobacco goes between about 2 and 5 pounds. And they even have the equation of the regression line. I can zoom in if you really want to see it. Well, that's about as far as I can zoom, I guess. They drew a regression line, and you can see it's an upward trend, and it does seem to be an association there. Okay. All right, well, doesn't always work. I mean, I'm fond of a beer now and then, but I never smoked before, so I wouldn't fit that one so much. But they did say, somewhere in here, they did finally say that the number was about a 0.8 correlation. I think they say that a little bit later. Yeah, so they haven't said it yet, but they will eventually say what the correlation coefficient is. So one does seem to be associated with the other, but it doesn't mean that drinking alcohol makes you smoke or smoking makes you drink. Maybe for some people it does, but we cannot directly say that. And we had some others. We talked about the dental visits, but we also had another one about running speeds of various animals versus their length. And so we have these animals that range from deer mouse all the way to a cheetah, and their length in inches, and then their speed in feet per second. And they put them on a graph, and then we see, oh, they line up very well. They line up quite well, actually. So let's see, they have a R number for that one. I don't actually see it. Perhaps they talk about it a little bit later. Um, yeah, so in the alcohol versus tobacco one, that was a 0.78. So going back here very quickly, we had 0.78. That was a pretty strong, although not up to the 0.8 for very strong. It's moderately strong, or you can just say moderate, like the book says. And so there's a moderate positive association or correlation between the two. Now here, I don't think they gave us the number. I'm looking for it. I can't find it anywhere. But I'd say that's about a 0.9 at least. So that's a very strong one indeed. So the longer they are, at least in this sample, the faster they are as well. And that just stands to reason. The cheetah is the fastest animal in the world. They have that at the Wild Animal Park, Safari Park down there in San Diego County. So anyway, they finally mentioned here 0.78 is a fairly strong correlation coefficient for what we see there. And yeah, so we have a bit of a summary to wind things up a little bit here. They carve out the deals, and we've already seen this picture before. But we had a few other topics about causation. For example, being bored could be bad for your health. Yeah, you don't want to be bored for very long. A little bit here and there is normal, but if you find you wake up bored every single day, you need to change something, or maybe several things. And yeah, positive correlation. We don't have the data there. We do have some other things to look at. Determining whether one event causes another event is more difficult than determining mere correlation. Correlation is the simple part. Two phenomena can be correlated without one of them causing each other. When two quantities are correlated, there are three possibilities. One causes the other. Yeah, like studying hard causes good grades most of the time. Or both are caused by something else, such as the warm weather and the sharks and the ice cream. Or the correlation could be just coincidence, just pure chance. So that's why getting bigger samples or more than one sample is a good idea. So suppose a mother notices that from time to time her baby gets a runny nose and a cough. Excuse me. The cough seems to come first most of the time, so she concludes that the cough causes the runny nose because the cough comes first. But in fact, most likely explanation is both are caused by a third factor, not warm weather, but the baby has a cold. The cold causes both the runny nose and the cough. They both are together. They're correlated, but it doesn't mean that one must cause the other. And they also flash back to the tobacco and alcohol, and they're positively correlated. And an increase in one generally causes increase in others. So if you smoke more, you're probably going to drink more. But I've met smokers who didn't drink a drop in their life, and I'm certainly another person who has the beer here and there, but I've never smoked before. So, and some people do neither, and some people do both. So that's up to you. You decide. But of course, the smoking and lung cancer, yeah, that's a classic case. It's been going on for decades. And many studies have shown that smoking and lung cancer are positively correlated. And it's indisputable that smokers have a higher rate of lung cancer, but the tobacco industry has argued that this does not mean that smoking causes lung cancer. It could be like the baby with a cough. There could be another cause for this. Not sure what it would be. Maybe living in a heavy smog area or something. But can they say that one causes the other? Maybe they argue there's a gene or some other unknown behavior that increases the propensity for both the smoking and the lung cancer. And it does require much more evidence to show that something is caused by something else. But enough research has been done to convince the medical community that smoking, in fact, indeed does cause lung cancer. So if you're smoking tobacco, probably a good idea to cut back or cut it out eventually, because it's just not a good thing. They call them cancer sticks, And California is second only to Utah in the lowest smoking rate of all. And yeah, so I was seeing a smoker over the summer, and that was uncomfortable for me. I'm not used to that, but she was still very nice. We were outside most of the time, but still, it's not a good idea. And here, there is no third lurking category, even though the industry was hoping there would be one. There really isn't any major one. Smog, or living in a smoggy area, or living near a plant or something that has lots of pollution, that would be a factor. But it cuts across the board, whether you live near one or not. Smoking tends to cause lung cancer. But of course, then I can talk about my great aunt, who was almost 90, and she made it almost all the way to the end, smoking 2 or 3 packs a day most of her life. And she lived to be I wouldn't say she was healthy at the end, but she was healthy within about a year of finally going on the machine and all that kind of thing. But some people have a more of a tolerance for that than others, but that's not part of our class, obviously. So let's go ahead and wind it up. I think I've gotten through several things. Plenty of homework problems you can do. The homework has answers in the back, the odd problems that is, and many of them are very popular. I used to assign a lot of these in the past, but I'm not doing it now. What I will do is to work through, and of course, there's a very good chapter summary. I'll talk a little bit about that coming up as we get ready for the final 6.2, 6.3 that we talked about, overview today, and then the effective drugs. And I'm going to work on the chapter quiz. So if you want to get started on that before you see the next video, which will probably be taped a week from Tuesday. That would be Tuesday the 30th. I don't have my calendar in front of me. Let's see if the last meeting is the 3rd. That means it'll be the 1st of December. Looks like that'll probably be recorded. And I'll work through all of these and a few more that I think that are pretty important as far as the final is concerned. Unfortunately, the standard deviation problem is tedious. So maybe I can find a easier one to do in parallel to that. So start looking at the chapter quiz. You don't have to turn in anything. But definitely don't skip the web assignment. That's just not enough help for you, I'm afraid. Be sure you get a lot out of the web assignment, but it may not be enough. So I'm trying to get you ready for the final. And obviously have your Zoom camera on. I cannot grade your test with your Zoom camera off. So, don't want to see you next semester. But anyway, that seems to be enough for now. It seems like I've run a little long today. So that's the recording for next Tuesday. And we'll be back probably recorded on the 1st of December. And more review, and then a live review on the 3rd of December. And I'll have your test results as soon as I can. I'm finally done with planning so I can start grading starting later tonight and tomorrow. Okay, that'll be it for now. Have a happy Thanksgiving, and we'll talk to you soon. Bye-bye.